Hello, welcome back to Engineering Circuit Analysis. We're doing three-phase circuits. We're working on the Wye-Wye circuit configuration. Here we have kind of an interesting problem. It's a little bit weird, but I'll explain why as we go. It says a Y-connected balanced load has a line voltage magnitude of 6,600 volts. The load impedance is given by this, 240 minus J, 70 ohms per phase. And it's fed from a line with an impedance of, and here's the impedance, 0.5 plus J4 ohms per phase. Now we're asked to find two things completely independent of one another. The first is we want to find the magnitude of the line current, and we want to find the magnitude of the line voltage at the source. This is an excellent problem to illustrate why I spent so much time before discussing all of the fundamental building blocks. Because, first of all, it's telling you it's Y-connected. You know what that means now. It's balanced. You know what that means now. All the load impedances, for instance, have to be the same. And then let me skip down a little bit. It's telling you the load impedance is 240 minus J70 ohms per phase. Now you know what that means. It means that the load impedances are all the same because it's balanced, and that's given by that. Notice that this is actually capacitive load. So it's not an inductive load, that's a capacitive load. And it's fed from a line with this impedance here as well, so many ohms per phase. Again, you now know, since it's balanced, that all three lines have the same impedance, so that makes sense. Right? So A, B, and C phase have this as a load. A, B, and C phase has this line impedance as a load. I'm sorry, as an impedance. So the interesting thing, or the weird thing about this problem actually, is that it's telling you, let's see, it's balanced, it has a line voltage. Now you'll understand what the concept of a line voltage is. When you see line voltage, you need to be thinking VAB. Basically, that's a line-to-line voltage. That's the terminology we use. Line voltage means line-to-line. VAB or VBC or VCA. Those are line voltages, right? But the weird thing about this problem is it only gives you the magnitude. It does not give you the phase information of that guy. And then also, it's telling you in what you're trying to find, it's not asking you to find the line current and the line voltage. It's just asking you for the magnitude of the line current and the magnitude of the line voltage. So you know when you write a phasor down, you have the magnitude, then you have the angle bracket with the phase inside, right? This problem is basically only asking you for the magnitude information. They're only asking you for how big the voltage is. They don't care about the phase angle. And what we're going to find is that as we get going in this problem, they don't really give you enough information to really concretely come up with the phase information for these answers, and that's why they're not asking you for them. So in a problem, when you see something like, find the magnitude of this, find the magnitude of that, usually they didn't give you enough information to find the phase of whatever those things are anyway, and that's why they're asking you for that. But you can make some assumptions along the way to kind of get from point A to point B. That's the challenging part of this problem. So the first thing we need to do for every problem, notice it did not ask you to draw a single phase equivalent circuit. It didn't ask you for that. But that is something you have to do. It's like back in basic physics when they give you a pulley problem. You have two pulleys and you're pulling on them and what happens or whatever. Or an inclined plane. You have to draw it, right? So the same thing for three-phase circuits. You have to draw it because there's no circuit given to you. So the first thing we're going to do is draw a single phase equivalent circuit. So we know that for every single phase equivalent circuit, we're going to have some kind of source. We don't actually know what that is, but we have some kind of source. And we're going to call it, let's call it V sub S, right? And we know that we're going to have some kind of source impedance. That's the impedance of the windings associated with the source. So we're going to call that Z sub S, the source impedance. And then we know that over here somewhere we're going to have well, I'll label it here in a second, but we're going to delineate between the line and the load. And the line, it says right here, let's see here, the line, it's fed from a line, 0.5 plus J4. So you have a resistor right here, and you know it's inductive because this is positive. And I'll label everything in just a second, but I want to do this in black. And then it says the load impedance is this minus this. So you know from that you have a resistive component and a capacitive component. I actually don't care what you write for these. You can put rectangles or boxes for these symbols. It doesn't matter. But you might as well look at the signs and figure out what it actually is. So here we have our circuit. Now let's go ahead and do some labeling. We know that this is just a single phase of the equivalent circuit, right? So we know that over here is really the neutral where the other phases are tying in. We call it capital N. And we know this is the neutral on this side where all of the other phases from the other sources are tying in. And we also know, since we're drawing the A phase, that this is A and this is B. I'm sorry, not B, it's capital A for A phase. Capital A and little a. And I'll switch colors to go ahead and write everything else down. So the line was 0.5 ohms.